So question 4 brings us on to group 2 and group 7. I can't emphasise enough how important it is that you learn the various bits of descriptive chemistry that relate to these two groups. It's a really important part of this module. They often hang a large chunk of the chemistry you need to know on the reactions of these two groups. In fact, this paper is unusually light in terms of the amount of it that there is. So if you haven't done that yet, that's a hugely important part of your revision. So, first up, we're looking at these displacement reactions in group 7. These are very important, and so before we get into the specific question here, let's just remind ourselves what's going on there. So, the idea is that you're setting up a competition, a fight, if you like, between two group 7 elements over electrons. So if we look at experiment number 1, that's described on the sheet there, we're adding Cl2, chlorine, to I-, iodide ions. So what we've got is two different halogens, chlorine and iodine, and the difference is that the iodine has already got extra electrons, which it got from somewhere. So it might be in the form of sodium iodide, and it got those electrons from sodium. Chlorine, on the other hand, has not yet managed to get any extra electrons. And the question is, when they meet, is will the chlorine be able to grab those electrons away from the I-? Well, the answer to that is yes, because what you have to remember is that as you go down the group, elements become less good at attracting electrons in their outer shell. Now you know that from all the stuff you've learned about ionization energies. Remember, the trend as you go down a group is that ionization energies decrease, and the way you explain that is because the outer shell is getting further away from the nucleus, more shielded from the nucleus, and that outweighs the increased nuclear charge, so the attraction to the nucleus decreases. Now, we're not actually talking about ionization here, because we're not talking about removing electrons from an atom, we're talking about gaining electrons. Nevertheless, the principle is very much the same, because it's still about attracting electrons into that outer shell. So, what happens is that chlorine is higher in the group than iodine. That means its outer shell is closer, less shielded, more attractive place for electrons to be. So when the chlorine makes a grab for the electrons from the I-, it will win. And so the consequence is that at the end of the reaction, what happens is that each of those I- ions will lose an electron, and Cl2 will turn into two Cl- ions. So you get this. Okay, Cl2 turns into two Cl-, and two I- turn into I2. Okay, so the golden rule that you have to remember is that the element that's higher in the group wins. In other words, the element that's higher in the group always ends up as the negative ion because it attracts electrons more strongly. So the question said, what colours would we observe at the end of each of these experiments? So what you have to decide in each case is whether a reaction will take place or not, and then, dependent on that, what the colour of the material in the tube at the end would be. Now the colours come from the elements, from Cl2 or from I2 or from Br2 in the other examples. The negative ions have no colours. They're always colourless solutions, so you can just ignore those. So in experiment 1, what we've decided is that at the end you have I2, and so the colour you observe will be the colour of iodine. What you have to notice is that it says the colour seen within the organic solvent. So what happens in these experiments is you do the reaction in water, that's what all the aqueous signs mean, but that at the end there's an organic solvent there, and whatever halogen is present at the end, you know, the element form, will move from the water into the organic solvent. And so the colour you see will primarily be in the organic solvent. And the reason you do that is that iodine gives a distinctive purple colour in an organic solvent. In water it gives a brown colour, which is sometimes hard to distinguish from the orange of bromine, and that's the reason for using the organic solvent, because then you can definitively say, oh yeah, that's definitely iodine, because it gives that distinctive purple. So that's the missing word for experiment 1, is purple. Experiment 2, we're adding chlorine to bromide. So the reaction this time is chlorine reacts with Br-, and again chlorine is higher in the group than bromine, so it will take the electrons away from bromide and so you'll end up with Br2 at the end, which is orange, as they've already told you. So that was experiment 2. Now experiment 3, we're adding Br2 to Cl minus. Okay, so this is actually rather different, because this time we're adding orange bromine to colour the Cl minus, and the ideas we've already had tell us that there will be no reaction, because chlorine is higher in the group than bromine. Chlorine attracts the electrons more strongly, so it will hang on to the extra electrons it's already got as a chloride ion, and the bromine will be unable to wrench them away from it. So we will still have unreacted bromine at the end. So the colour you see in experiment 3 is again orange, because the bromine hasn't reacted. Okay, so in the little table you should have purple, orange, orange as you read down. Okay, so now we want the ionic equation for the reaction taking place in experiment 2. So we've already written this up once, but let's just remind you of that. An ionic equation means you only include the ions that are actually involved in the reaction. So it doesn't even tell you where the iodide and bromide and chloride ions came from. You know, it could be sodium iodide or potassium iodide or whatever it might be. And that other ion is irrelevant, because it's just not involved in the reaction at all. It just floats around in the solution, not doing anything. So in an ionic equation, you leave ions like that out of the picture, and you only include the ones that actually react. So the equation we had was Cl2 aqueous. You don't actually have to put the state symbols in here, but since they've put them in the experimental details, it's a good idea to include them. So Cl2 reacts with 2 Br minus to give you 2 Cl minus plus Br2. And that's the ionic equation for experiment 2. Now part 3 is asking us to come up with another experiment which we need to confirm the order of reactivity. So let's look at the evidence we've got so far, and then we can see what's missing. So experiment 1 told us that chlorine was above iodine, okay, because chlorine managed to grab the electrons away from I minus. So chlorine is higher than iodine. Experiment 2 told us that chlorine was higher than bromine, because it managed to grab the electrons away from Br minus, from bromide, which tells us that. Experiment 3 confirmed that chlorine's more reactive than bromine, because the bromine failed to grab the electrons away from Cl minus. So from those 3 experiments we know that much, but crucially we don't know what the relative order of reactivity of iodine and bromine is. Now we know theoretically what it is. Bromine's higher in the group, so it should be more reactive, more able to grab electrons. But we need an experiment to confirm that, and the experiment needs to show the bromine taking electrons away from I minus, because that would confirm that bromine's more reactive, more attractive to electrons. So to do the experiment you need to add bromine to I minus. Okay, so aqueous bromine to aqueous I minus, and the result would be that the bromine would grab electrons from the I minus, so iodine would be formed. And so we'd see the purple colour in the organic solvent. In fact, to get the marks, all you had to say was that you would add bromine to a solution containing iodide ions. But it's important you realise that what would happen there is that the iodine would be formed, and that you'd know that because it was purple, and that would confirm that bromine was a more reactive element than iodine. Okay, part B then is the chlorine plus water story again. So again, this is straight out of the syllabus. You shouldn't really have to do much thinking here, because you should have learnt this reaction. So the equation is Cl2 plus water goes to HClO plus HCl. So it says, using oxidation numbers, explain why this is a disproportionation. So that means you've got to go through and assign oxidation numbers all the way across there. So remember to do this very clearly so they can see the oxidation numbers for each element, and then, having got the numbers, you need to use them to show what was oxidized and what was reduced. That's always the way to do these redox reactions. So, chlorine, the oxidation state is 0. Remember, unreacted element, like Cl2, the oxidation state is the baseline, 0. In water, hydrogen in compounds is always +1. When it's H2 gas, it's 0, but otherwise, you can say that in a compound, it's always +1. So we've got 2 lots of +1. And I write it like that to emphasize that the oxidation state of the hydrogen is +1, but we've got 2 of them, and that's important when we come to balancing up oxidation states. In this case, you actually don't need to do that because oxygen in compounds is always -2. So again, you can just write that one in. But notice that the sum of the oxidation states adds up to 0, which it must do because in a neutral compound, the sum of the oxidation states is always 0. So 2 lots of +1 added to the -2 adds up to 0. Now here is where that idea becomes important, because the hydrogen is +1, because in a compound it always is. Oxygen is -2, because in a compound it always is. Chlorine can be all sorts of things. It depends what it's bonded to. So that's the point. There's no rule that says chlorine is this. You have to work it out, and the way you work it out is by making the sum of those oxidation states 0. So far we've got +1 -2 takes us to -1. So in order for it to add up to 0, the chlorine has to be +1. On the other hand here, again the hydrogen is +1 because the rules tell you it always is in compounds. So this chlorine is different, because in order for these to add up to 0, this chlorine must be -1. So you get the point that chlorine is the interesting element here, because its oxidation state changes. It's 0 at the beginning, but in the product, some of it's become +1, some of it's become -1. So what you now need to do is to say, well, when it goes from 0 to +1, the oxidation state is getting more positive, and that means that oxidation is occurring. Okay, so if the oxidation number becomes more positive, that means that element has become oxidized. On the other hand, at the same time, another portion of the chlorine is going from 0 to -1. So that's getting less positive. And getting less positive is reduction. Okay, so you need to learn those definitions of oxidation and reduction. More positive is oxidation, less positive is reduction. So why is it a disproportionation reaction? Because one portion of the chlorine is being oxidized, but another portion of the chlorine is being reduced in the same reaction. That's what disproportionation means. Alright, what's the benefit for public health of that reaction? That the solution of chlorine in water kills bacteria, so it's used in swimming pools and in tap water at lower concentrations to make sure they're safe to drink, because they kill harmful bacteria. Alright, part C, we're switching attention now to group 2, and focusing first of all on this reaction where you heat magnesium carbonate and it breaks down into the oxide plus CO2. So this is a reaction which again is straight out of the notes. You need to learn this. And what's it called? The answer is thermal decomposition. Okay, and you need both of those words in there. They wouldn't accept just decomposition. So thermal decomposition is what it's called. And then there's a little calculation which is to figure out what volume of CO2 would be produced. So the first thing we've got to do is to figure out, as always, how many moles of material we've got, and it tells us that we've got 1.47 grams of magnesium carbonate, so we can turn that into moles. Okay, so we get moles equals the mass over mR, which is 1.47 divided by 84.3. It gave us that value. Again, always scan the question, because you could have added it up yourself, but it's all precious time wasted, and you know that these papers tend to be a race against time. So 84.3 is the MR, and if you calculate that number, you get 0.0174 moles of MgCO3. And you say, okay, but we're interested in the carbon dioxide, so how does that come in? Well, then you go to the equation. And remember, that's so often the case. You should really expect that to be a likely thing to have to do in a question, is first to work out the moles of one thing, and then to say, right, now we know that, we can go to the equation to relate that to moles of the other things. And you can see in this case it's absolutely straightforward, because each mole of magnesium carbonate, when it decomposes, gives a mole of CO2. So it's just 1 goes to 1. So you can say that the moles of CO2 formed is equal to the moles of MgCO3, which is 0.0174. And the final thing is we've just got to turn that into a volume. So gas volumes is another of these mole relationships that you just have to know. And the relationship is that the volume in dm cubed of gas, and you can obviously only apply this to gases, is equal to moles times 24.0. Again, that number is on your data sheet. It tells you on the back of your periodic table that 1 mole of any gas occupies 24.0 dm cubed at room temperature and pressure. So what that means is that you can just take this number of moles, multiply by 24.0 and get 0.418 dm cubed is the answer. And again, always check the units. In this case, it does want the answer in dm cubed, so you don't need to do any more. Had it asked for it in cm cubed, which it sometimes does, you would have had to multiply by 1,000. So always check carefully that you've thought about the units. And the final question is just this trend that you have to know. You can't easily figure this out, but you just have to know that as you go down the group, the carbonates become increasingly stable to heat. Okay, so the answer is that the group 2 carbonates become more stable to heat as you go down group 2, or the ease of decomposition decreases as you go down the group. Okay, so that's it, group 2, group 7, make sure you learn it.